Okay guys, we are continuing here at the tech stage. So that was a really interesting panel discussion that we had from the different L2s. And yeah, that was like the end of our whole chapter about layer 2 scaling solutions, all their challenges, problems, and so on. And now we're going to the next talk, which is not less interesting. I'm really looking forward to it. And I'm welcoming our next speaker here, which is Linus, and he's the creator of BITVM. And yeah, the stage is yours.
Thank you. Thank you. Hi everyone, my name is Linus. I'm going to talk about BITVM, which is a way to enable smarter Bitcoin contracts, and in particular to build better Bitcoin bridges to second layers. First of all, the motivation, why are we doing this? We would love to scale Bitcoin to billions of users. Probably everyone knows the capability of blockchains is limited, and the best scaling solutions that we know so far is second layers. On altcoins, there is like huge research efforts going on. On Bitcoin, there is Lightning Network, which works quite well, and it's probably one of the most used L2s, but it's quite limited. It doesn't scale as much as we would like it to scale, and that's why we are searching for better scalability solutions. And that all starts with how to bridge Bitcoin to other systems. This is, it's lagging. So the big issue is that the Bitcoin blockchain doesn't scale very well, so most users won't be able to afford main chain fees in the long run. And so we would like to have BTC, the Bitcoin native currency, on sidechains, on rollups, on other second layer protocols such as CK coins, which enable privacy and larger throughput. And if we had that, that would enable rapid innovation and also cheap experimentation. And all these L2s ideally would be interconnected via Lightning, so that the end user doesn't even care on which L2 they are. They can pay anyone on any other L2, irregardless where they are. However, the big problem is how to build better bridges. Currently, the best we can do is multi-sigs, and BITVM is a way to enable better bridges. That's the main idea behind it. A quick overview about the talk. I'm going to start to talk about stateful scripts, which means how to introduce state into Bitcoin, even though Bitcoin is actually inherently stateless. Then we're going to build BITVM on top of stateful scripts, and on top of BITVM, we're going to build a bridge. I'm not sure if that should happen. Okay. So that's roughly how the talk is structured. First of all, stateful scripts. How do we introduce state into a stateless system? The first hack to introduce state into Bitcoin is by using signatures. So the rough idea is, if we could just sign an arbitrary value for, if we could verify the signature for an arbitrary value, then we could enforce to have a particular value, let's call it X, in script 1 and in script 2. So script 1 checks the signature for a particular public key, and script 2 checks the same signature, and this would be already enough to ensure that we use the same value for X in script 1 and in script 2. And that's a way to transfer state from one script execution to another. So for example, Alice signs that X equals 42 in script 1, and script 1 can only be executed if Alice actually provides some kind of signature. And then Bob can observe the blockchain and see that signature and use that signature in script 2 to unlock script 2. And Bob cannot change the value of X. because he cannot forge a signature of Alice. So he has to use the value x equals 42. And the good thing here is Bob could be anyone. Anybody who could who observes the blockchain can see Alice's signature and can then extract that signature and execute it, or like use it to execute script 2. The big problem here is though, how do we verify a signature in Bitcoin script? Bitcoin script does verify signatures for transactions. However, the message that is signed there is just the hash of the transaction. You cannot verify signatures for arbitrary values in Bitcoin script. Actually, you can. If we would have check signature from stack, then it would be easy. However, we don't have it yet. So the nice workaround that we can do is using Lamport signatures. Lamport signatures are conceptually very simple. They are based only on hash functions. They don't require any complex like elliptic curve operations or something like that, just hash functions, that's it. And they are so simple that they are possible in Bitcoin script as it is right now. And the main drawback of them is they are quite large. You need lots of hashes even for small messages. However, they're small enough to fit into Bitcoin transactions, and then we can use them to sign bytes, to sign 32-bit words, and even to sign hashes, and that's actually all we want, or all we need. Here's a quick demo how a Lamport signature for a 1-bit message would work. Let me see if I can, yeah, here I can point. So we have two hashes here. This is, let's call it hash 1, and this is hash 0. And to unlock the script, you have to provide a pre-image. Either you provide the pre-image for hash 1, or you provide the pre-image for hash 0. If you provide the pre-image for hash 1, then this path will be executed, and it will leave a 1 on the stack. If you provide the pre-image for hash 0, then you will have a 0 on the stack in the end. And if you don't know the pre-image, if you provide something incorrect, then the script will just fail. And that gives us a signature for a 1-bit message. And in theory, we can just copy this n times, and that gives us an n-bit Lamport signature message. A Lamport signature for an n-bit message. And I guess most of you are not that familiar with Bitcoin script, so I won't go too much into detail now. But what you can see here is we need, just for a single bit, we already need like two hashes in the script, and this blows up quite a lot, actually. But still, these Lamport signatures are good enough to do all kinds of interesting things. There are also lots of optimization possible. For example, we can use Winternet signatures, which is essentially just an optimization of Lamport signatures, but the key idea stays the same. The second way to introduce state is by using connector outputs. What's a connector output? Well, it's an output for a so-called conditional transaction. So here we have Alice. She has an output here, and she pre-signs this transaction, this conditional transaction, but she doesn't pre-sign only her own output, she also pre-signs this output. And essentially that expresses that Bob can take her money exactly if the condition transaction happens. If the condition transaction does not happen, then it's impossible to execute the conditional transaction, because that conditional transaction commits to this output here, which is created by this transaction. And this is actually super simple, but quite powerful, because we can use it in conjunction with another transaction. Here it's called the alternative transaction. And if for some reason the alternative transaction happens, then this connector output is consumed by the alternative transaction, which renders the conditional transaction obsolete. So it essentially expresses Bob can take the money if the alternative transaction doesn't happen. It seems to be very simple, but this is an extremely powerful mechanism that is kind of like the heart of the Bitcoin bridge later on. I'll come back to it in a later slide. Here, this is rendered obsolete by executing the alternative transaction. So, rough overview about the BITVM architecture. The paradigm in general is using optimistic execution, optimistic computation, which means there's one party, we call it the operator, and the operator just makes a claim. They claim, hey, the state of the system is X, and if that is correct, then everybody is just fine with it and nothing really happens on the chain. It's essentially just a regular transaction. However, if it's incorrect, then you can go through the entire BITVM setup and disprove them. So you never prove something that is correct, you only disprove something that is incorrect. And that is quite a powerful approach, because in most cases, or like in the regular case, it will be quite cheap to execute it, and only if there's somebody who wants to cheat and who wants to lose their money, then you have to execute all the heavyweight stuff. Oh yeah, in general, it's also much easier to disprove a faulty execution than to actually compute the result. That is another thing that is very helpful here. And we combine that with a snark verifier. I hope you are at least roughly familiar with how proof systems work, or about the nice compression features that they enable. Snark is one of the hottest topics in the entire crypto space, I would say, because snarks are so powerful. And we are using here a snark in the BITVM, and that combination gives us a very powerful system. Okay, then how do we express advanced Bitcoin scripts? We implemented a high-level language on top of Bitcoin script. So our high-level language compiles down to Bitcoin script and to graphs of transactions, and that lets us allow to express all kinds of complex statements. It's essentially a templating language for script that just adds a couple of features, like for example loops. If you're familiar with other smart contracting languages, loops is actually the most simple thing, but Bitcoin script is intentionally not Turing complete, so there are no loops. But we can unroll loops as long as they have like a static bound. So if we know it is running for, I don't know, 10 times, then we just copy the same code 10 times in there. And this templating language does that under the hood, so you don't have to care about it. Yeah, you can compose functions, and there's also like a huge library of precompiled opcodes for XOR, shifts, multiplication, also hash functions, and as well field arithmetic, and all kinds of nice high-level things that you probably know from other scripting languages, such as the Ethereum thing and so on. And yeah, there's all kinds of primitives for statefulness. In particular, the things that I mentioned, there's like high-level primitives to use Lamport signatures, and there are high-level primitives for connector outputs. And this nice language allows us to essentially implement BITVM in the end. Yeah, and that usually leads to complex scripts, complex tab trees, and complex graphs of transactions that then encode the contract that we want to encode. In Bitcoin, everything is a bit clunky, and yeah, this language allows us to formulate contracts on like a high level and then compile it down to yeah, the scripts and graphs of transactions. So how do we use that to build bridges? First of all, like quick overview, the idea is to bridge BTC to any other system, to sidechains, to Ethereum, for example, but also in particular to all kinds of L2s, such as rollups and ZK coins that I mentioned. And the rough idea behind it is fine if the bridge is a bit clunky, because even if it's slow and costly, it's still incredibly valuable if we can bridge BTC to another system, because once we have some kind of bridge that guarantees that the sidechain asset has value and can always be redeemed for real BTC, as long as we have that, then we can have atomic swaps, and regular end users can just use atomic swaps, in particular via Lightning, and they don't have to use the bridge at all. They have the guarantee that the sidechain coins are valuable because it's always possible to redeem them thanks to the bridge, but they themselves don't have to use that. So it's just a matter of reducing trust. And yeah, it's fine if the bridge is only used for large amounts because we have atomic swaps for regular users. Yeah, and one major drawback of that bridge is that there is a fixed set of operators. So during compile time, we have to determine a set of operators who will operate the bridge for everyone. But the good thing is everyone can be a verifier, so you don't have to trust the operators. You have to trust them for liveness, but you don't have to trust them for safety. They cannot steal as long as there's any user who cares about the system. Yeah, the guarantees more concretely. It is a federation, but a single honest member suffice. There's a trusted setup where we can have about 1,000 co-signers. And then there's roughly 100 operators. And the guarantees are that the bridge is safe, so nobody can steal deposits. If one of the 1,000 co-signers is honest, then we have the guarantee of safety. And the bridge is live, so eventually any packout will be, nobody can stop a valid packout as long as one of the 100 operators is honest. And the operators, they are competing for fees, so they are incentivized to be live. And a nice thing is that, in theory, you can become a member, so then you don't have to trust anyone because you are that one honest person. Of course, in practice, not everyone can become a member, but everybody who is like a large liquidity provider or an exchange or anybody who has like a high stake in the site system can just participate in that ceremony, and then they, from their perspective, the system is completely trustless. Here is like a rough overview of the transaction graph, in particular like how the bridge works. It's simplified, but it roughly shows how it works. We start here. Alice packs in 100 BTC, and she pre-signs this pack. The committee, the N of N, the 1,000 people that I mentioned, they pre-sign this packout transaction. And this packout transaction just gives the 100 BTC here to the operator. This is a simplification, and for now we will just keep it here, keep it like that. I will show in a later slide how to get rid of that constraint. But the rough idea is we have that pre-signed packout transaction which commits to these two outputs. And these two outputs come from the kickoff transaction of the operator. And it essentially says, the operator says, hey, I witnessed a valid packout, so I'm going to put my kickoff transaction on chain. Then he has to wait for 6 months before he can spend this output, essentially making him wait 6 months before he can process the packout transaction. And then there is this connector output. And this connector output is also pre-signed for this transaction. And this transaction is like the final transaction of the BITVM game between a watchtower and the operator. This is a black box for now, but the rough idea is if the watchtower wins against the operator, so if the watchtower disproves the claim of the operator, then the watchtower wins an output that allows them to execute the slash transaction. And by executing the slash transaction, they burn this connector output, essentially rendering the packout transaction obsolete. So the operator will not be able to touch the funds if he's lying. That's the rough idea here. So if he's lying, then he will lose this game. The watchtower will execute the slash transaction, the connector output will be burned, and the packout transaction cannot be executed because it commits to all these 3 outputs, and it can only be spent with all the 3 outputs. And if one is missing, then the packout transaction is impossible to execute. So that's the rough idea how the bridge mechanism works. Of course, here is a huge black box, and we are going more into detail now how this black box works under the hood. So, yeah, that black box is essentially a snark verifier. we are using like a pairing-based proof. We have implemented both gross 16 and flonk. And the huge problem is that a flonk implementation in Bitcoin script, even if we optimize it as crazy as possible, it's still like roughly a gigabyte. And a gigabyte of script is of course way too large to execute it on Bitcoin. The Bitcoin block size is 4 megabytes, so it's absolutely impossible to execute a script of 1 gigabyte in one chunk. So what we are doing is we simply commit to the trace of the execution of like 1,000 intermediate results, and then we split up. Let's say we have a function called f, and let's say this is our snark verifier, and x is a proof, and y is some state that this proof is proving. F is too big because it's, as I said, like a gigabyte or even more than a gigabyte. So what we do is we split it up into smaller chunks, and each of these chunks produces an intermediate result, these z1 to zn, and every intermediate result is the input to the next chunk. And so we chunk it up into many parts, and then we have f chunked up into like 1,000 subscripts. And each of these subscripts is just a couple megabytes, and that makes them small enough to execute them on chain. And the good thing is we don't have to execute all of them. We just execute a single one, and we execute exactly the first one that is incorrect. Because what we want to do here is we just want to disprove a lying operator. If the operator was honest, then there is no need to execute anything. Only if somebody was lying, then we have to disprove them. And if they were lying, then that means one of these f's was executed incorrectly. So we pick out that f that was executed incorrectly, and then we execute this f, compute the correct result, and then we show that the result which the operator claimed is incorrect. So disproving a single step suffices. So we don't have to execute a gigabyte of script, we just have to execute a megabyte essentially. Yeah. For example, if f42 of z41 is not z42, then we execute f42. And yeah, each of these subscripts can be 4 megabyte because that's the block size. So we have in total 4 gigabytes of script that we can execute using this mechanism, and that is more than enough to execute flonk or gross 16 or other pairing-based verifiers.
Would you need a full block for executing?
Yeah, like if the script is 4 megabyte, then you would need an entire block to execute it. Yeah.
How high is the possibility to get just a full block just for the script?
Well, it's a matter of fees, right?
Exactly.
Yeah.
Quite expensive, right?
It is expensive. The operator has to make a commitment. They have to put up a deposit, and essentially they are betting that nobody can disprove them. And if you can disprove them, then the operator pays the fees for you to disprove them. Yeah, that's an important point. And yeah, of course, this aligns the incentives such that the operator will not lie, because it's just stupid to do so. Here's a bit more complex graph that implements more of that logic. Now the black box is gone, and we have here these, here in particular is the heart of the verifier that I just described. And here is the commitments that the operator makes. So he commits to the proof itself, and he commits to the 1,000 intermediate results. And then here is a huge tab tree with 1,000 possible scripts. And if the operator was lying, then you can disprove them by executing one of the scripts. For example, here the subscript 42 was incorrect. And the rest is basically the same as we saw in the previous picture. So here's the peg-in, and the committee pre-signs this take transaction, the peg-out transaction, and sorry, take transaction. And here the operator fronts the capital and just pays back Bob. Like Bob was the guy who was doing the peg-out here, He did some valid peg out in the sidechain, for example. The operator witnessed that, and then the operator gives his money to Bob, just fronting him. And doing that entitles the operator to take money out of the bridge here. So he puts the kickoff transaction on chain, then he has to wait for 2 weeks. If his proof was incorrect, then anybody can challenge them just by executing the challenge transaction and burning the connector A. Because if the connector A is burned, then the take one transaction is impossible to execute. Essentially forcing the operator to go down here the unhappy path, where he has to make that commitment, and where you can disprove him if he was incorrect. If he was correct, and if the verifier was malicious and challenged him for no reason, then he can execute the take two transaction after 2 weeks. But otherwise, he gets disproved, and he will not be able to touch the funds here. So this is roughly the idea behind the Bitcoin bridge, using the BITVM2 paradigm in here. Probably the most important slide, the limitations. The main limitation is, of course, the complexity. If you compare this to like a Solidity verifier or something, it's like orders of magnitude more complex. Also, just implementing a snark verifier in this clunky Bitcoin script language is just a huge pain. That is the main limitation of this approach. The other thing is we have to balance incentives. It was already mentioned. The loser should always pay the winner's fees plus a bounty. So anybody, like if somebody is lying, then other people should be incentivized to disprove him. So they should make a profit from disproving him. So incentives have to be aligned there. And fees are not static. The fee market is fluctuating, and we have to guess in advance what the maximum fee is. Otherwise, the incentives are not as balanced anymore, and that could lead to failure of the system. However, if the incentives are balanced, the chain is not needed at all. All this stuff is not needed at all if the incentives are balanced, because then there is just no reason for anybody to lie, because they will just lose too much money, and then they will just don't do it. And we have observed this in other systems. I think Arbitrum or something. It just rarely happens it just never happens that somebody makes an incorrect claim just because it's so expensive. The next limitation is, of course, that the operator has to front the capital for 2 weeks. That is a capital cost that has to be covered by the fees. So the guy who is doing the peg out has to pay the operator for fronting that capital, and that is a cost that has to get paid, which makes the system inefficient in that way. It's not too bad, it's just 2 weeks, but yeah, as we know, Bitcoin is fluctuating a lot, so having to hold Bitcoin for 2 weeks is a cost. But the main improvement here is that no one-to-one collateral is required. There are already Bitcoin bridges that work with like over-collateralization, but here just a marginal amount of collateral can secure essentially infinite amount of BTC. So you could secure, I don't know, 1,000 BTC or even more with just less than 1 BTC. Then there's that setup. That setup is expensive. All the 1,000 parties have to pre-sign 100 peg-out transactions. So for each of the operators, all the 1,000 parties have to pre-sign. All of that can happen off-chain, but it is definitely a cost, and it makes the peg-ins slower than we would like them to be. And another issue is that the federation can censor peg-ins. Because of that requirement that the federation has to pre-sign these transactions, they also can just refuse to sign, and then the peg-in doesn't happen. However, nobody's losing money then. You just cannot peg into the other system. That's it. Summary and outlook. BITVM enables smarter Bitcoin contracts. In particular, we can build trust-reduced bridges for L2s to scale Bitcoin. And the main limitation is that it's practical, but the main limitation is that it's clunky, but it's still practical. The main, what makes people so excited about it, what makes people excited about it is that it requires no soft fork at all. It's possible with how Bitcoin is currently. However, it would be cool if we had a soft fork, for example, for TX hash. If we had TX hash, we could get rid of that trusted setup. That would be quite nice. No pre-signing would be necessary. Also, if we had an opcode for multiplication, that would be super great. Currently, we are emulating multiplication, and it costs like kilobytes of script to emulate just a 32-bit multiplication, which is a huge pain. And ideally, we would have something like block hash, which would allow us to do introspection, blockchain introspection, so that we can reason about stuff that happens in the chain. We have completed a very simple draft version of it, but it's not very useful other than for research purposes. However, we plan to release a reckless mainnet version by the end of this year. Hopefully, fingers crossed. Yeah, that's it. Thanks.